This is AP Calculus AB, and in this video I'm going to talk about section 6.2, and in this section we're going to be discussing definite integrals. So the last couple of classes, what we have been focusing on is the idea of a rectangular approximation. And so what we're going to do today is we're going to transition from a rectangular approximation, which is essentially approximating the area between our function and the x-axis. We're going to go from that idea into actually finding the exact value for those areas, and that'll sort of transition into the idea of an integral. So the first thing that you see here, this graph, what we're showing here is, let's imagine just for the sake of understanding what's going on here, let's imagine that this curve is a velocity curve, and we were trying to find the displacement. So we kind of saw how that would work before with the velocity, and if we integrated the velocity function, then it would tell us how far we had moved. Well, here we've got negative velocities and we have positive velocities. But if we were able to figure out what the area is, where we have negative velocities, and then figure out the area where we have positive velocities, we could find the displacement by figuring out the distance we moved forward and subtracting away the distance we moved backward. And so what's drawn on here is just some rectangular approximations. So let's say we just have some subintervals, and you can see as we start here at C1, we've got a rectangle drawn there, and it's below the x-axis. So essentially we would be moving to the left because we've got a negative velocity. So these rectangles here are supposed to be approximating how far it moved to the left. We've got 4 rectangles there. It looks like we're using primarily a midpoint approximation, but this is sort of a mixture of approximations because they're just kind of randomly throwing some rectangles in there to try to approximate what that area is. And then you can see once we cross over this point x sub k minus 1, now my velocity becomes positive, and from there we've got rectangles that are above the x-axis, and if we were to find those areas, that would be the distance I traveled in the positive direction. So the end result of this is, if I were to integrate the velocity function, what it would do is it would take those rectangles above the x-axis, treat them as a positive. The rectangles below the x-axis would get treated as a negative, and that would approximate the end result. Now, in order to make this more accurate, like we talked about in section 6.1, what we can do is we can put more rectangles in there. We can make these subintervals smaller. And that's really the idea of integration, is to make these subintervals get so small that our approximation for the area between the x-axis and the curve, that approximation starts to approach the actual value as the width of those rectangles gets smaller and smaller and smaller. Okay, so that's what this notation is showing. If we take the limit as the width of those rectangular partitions approaches 0, and we sum up all of those pieces, remember we talked about the summation notation last time, then that's going to be equal to the integral value. So I is just our integral value. So all continuous functions are considered to be what we call integrable. That means you can take the integral of them. And this is just notation that we're going to use. So we saw this when we were doing rectangular approximation. We kind of saw a notation like this, but what we didn't really focus on a lot was this idea of taking the limit as n goes to infinity, where now instead of just having like 6 rectangles or 10 rectangles or 20 rectangles, this is saying let's take the limit as the number of rectangles approaches infinity. Well, if we do that, that is an integral. And if we're doing this on the interval from a to b, this is the integral notation that is essentially shorthand notation for that summation we were writing before. So this is telling me the integral from a to b of f of x dx, and that is just basically a bunch of rectangles being added together, but we're making the width of the rectangles get infinitely small. Okay, so when we are looking at these, there's some vocabulary that we need to talk about. One of them is the limits of integration. That just sort of tells me my left bound and my right bound when I'm doing my integral. And then there's also this idea of an integrand. So let's take a look at just a quick example here. So we've got this summation written out, which is just a rectangular approximation again, but we're taking the limit as n goes to infinity, and they told us it's on the interval -1 to 3. Well, -1 to 3, those are my limits of integration, and you're always going to see those written on your integral. Okay, so that means my area that I'm looking at is bounded between -1 and 3. And then the integrand is this part of it. And that's essentially the function that I'm going to integrate. Now you notice this dx here and the delta x, those are really interchangeable, but even though I've written this now in an integral notation, I'm still looking at the base, which that's the width of my rectangle, times the height. Those are all of my function values. And then the integral is just adding up all of the rectangles as the width of them gets infinitely small. So it still means the same thing, it's just slightly different notation. Okay, so like I was mentioning earlier, we can think of the integral in terms of area. So when I have a positive function, so here it's calling this function non-negative, meaning that it could be 0, but it's going to be either at or above the x-axis when you look at a graph. And if it's integrable over the interval a to b, then the area under the curve is just going to be equal to the integral value. So I'm going to show you an example of what this means, because that's a little bit confusing when you see all of that vocabulary. It's kind of hard to understand what they're trying to get at. So here we're trying to integrate from -2 to 2 the square root of 4 minus x squared dx. So keep in mind that my function is right here. That's the function that I'm trying to integrate. If I were to graph that, so think of it as y is equal to the square root of 4 minus x squared. You may not recognize that right away, but if I were to square both sides, we'd have y squared is equal to 4 minus x squared, and that's the same as x squared plus y squared is equal to 4. Well, now you probably recognize that a circle with a radius of 2 centered at the origin. The only piece of this that we have to be careful about is that since we have essentially a positive here, that means we're looking at the top half of the circle. Because if we solved this equation for y, we would get y is equal to plus or minus the square root. The positive square root's the top half of the circle, the negative square root's the bottom half. So essentially what we're looking at here, if I were to graph this, would just be from -2 to 2, and I'm just going to mark this all off. I would have a semicircle that looks something like that, and my integral is just going to find that area right there. So since this is a really, really basic shape, we don't even have to do anything with antiderivatives or know anything about how to solve an integral other than understanding conceptually what an integral means. So that area that I have shaded in there is what we're trying to find. Well, that's just a semicircle, so I'm just going to do 1/2 times pi r squared. My radius there was 2, so that's half the area of half of a circle with radius 2, and that would give me a value of 2 pi. So that integral has a value of exactly 2 pi. So whenever your area is above the x-axis with an integral, we treat it as a positive. Whenever the area is below, we treat it as a negative. Okay, so like it says here, if the function is less than or equal to 0, then the area is the negative of the integral. And we'll go through one like that a little bit later on, and we'll look at this next one just to kind of clarify that a little bit. So let's say we're looking at some integral from a to b of f of x dx. We always do the area above the x-axis minus the area below. And in order to understand that, that's why I was talking about a velocity curve with that first example, because if you think of it as a velocity curve, it makes sense if I find the area where my velocity is positive, that would be where I'm moving in the positive direction. That's going to be positive displacement. And then the area where my velocity is negative, I'm going to treat that as a negative because that would be negative displacement. Okay, so here's an example of that. We have an integral from -2 to 3 of 2x dx. So if I were to graph that, this is what it would look like. So I've got this graph. Everybody knows what 2x looks like. So a very simple graph. And I've just got this linear function coming through here, and we'll just say that it has a slope of 2. Okay, so I'm going from -2 to 3. So we'll say -2 is about right there, 3 is about right there. So what I'm looking at from an integral perspective are these areas that are in here. So that area that I have above the x-axis would get treated as a positive. This area that I have here below the x-axis would get treated as a negative. So when I evaluate this, for today, we're just going to do this with simple geometric shapes. There's actually a way we could do this with antiderivatives. Some of you may have seen it before. That's not our focus for today. For today, we're just going to evaluate these using areas. So when I think about these with areas, well, if I were to find when x is equal to 3, the y value would be 6. So the height of this triangle is actually 6. When x is equal to -2, my function value would be -4, so the height of that triangle would be 4. So now if I'm going to evaluate the integral, I'm going to deal with the part that's above the x-axis first, 1/2 base times height, 1/2 of 3 times 6. That's positive. And now I'm going to subtract away the area that's below the x-axis, so that would be 1/2 of, it has a base of 2 and a height of 4. And I know it has a function value of -4, but I'm just thinking about this as an area. I've already accounted for the negative by subtracting. So in the end here, I have 9 minus 4, which is equal to 5. Okay, so my net result, let's say that were a velocity function. If that were my velocity function and I said, what's the displacement on the interval -2 to 3? Well, the displacement would be 5 units. Okay, so now let's look at just a few transformation rules, because sometimes on these problems we can use transformation rules to solve similar integrals to ones that we know. So what we're going to do for this one is we're going to assume that we know this integral, and I'm going to circle it here because I almost wrote over it. So we're going to assume that we know this integral is true, and you can see it graphed over here. So if we integrate the sine function from 0 to pi, we get a value that's exactly 2. So they're talking about that area right there, that shaded region. That shaded region has an area of 2. Okay, so knowing that to be the case, then there's some other integrals off of this. Like, for example, if that's 2, what about the integral from pi to 2 pi? Well, knowing what the sine function looks like, I know that once I cross over pi, now it's going to have that same shape below the x-axis. So that's going to give me a value of -2. If I were to look at 0 to 2 pi for the sine function, I would have this area that I can see above, that I would have an integral value of 2. I would have that area below, that would be, from pi to 2 pi. That would have an area of 2, but I would treat it as -2 from an integral perspective. So the net result of this would be 0. If I were to go from 0 to pi over 2, well, pi over 2 is just essentially right there. So I'm looking at half of that region that's shaded. So that would just be equal to 1. Now, if I were to start doing things like 2 plus sine x, there's a couple of different ways to look at this. But really what we're doing is we're translating that region up by 2 units. And when we translate it up by 2 units, essentially what we're going to do is we're going to create a rectangle of material underneath, or a rectangle of area underneath this curve that we have right now. So there's 2 ways to approach this thing. One is to think of it as a rectangle plus the area that I have. The rectangle would have a height of 2, and it would have a base of pi units. So in the end, I'm going to get 2 pi plus 2. Now, there is an integral property that we're going to learn where you can actually break integrals apart into pieces. We can actually make this the integral from 0 to pi of 2 plus the integral from 0 to pi of sine x, and that would allow us to solve it as well. But in the end, the easiest way to think about it from an area perspective is anytime we translate up, we're creating a rectangle of area underneath what we have. Okay, so now let's look at some transformation rules. If I go from 0, this is number 5. If I go from 0 to pi of 2 sine x dx, remember multiplying by 2 is a vertical stretch by a factor of 2, a vertical dilation by a factor of 2. So that means all of my y values are going to double. Nothing changed about my x values. So from an area perspective, that's going to double the area, and that's going to give me a value of 4. All right, so the next one here, we have sine of x minus 2. So if you think back to Algebra 2 and Pre-Cal, that would be a translation of the sine graph 2 units to the right. Now look at the limits of integration here. Originally we had 0 as the lower limit. Now we have the lower limit of 2. So we've gone 2 units to the right. Originally, we had an upper limit of integration of pi. Now we're at pi plus 2, so we've gone 2 units to the right. So essentially, everything here has just taken that graph that we see, it's been shifted 2 units to the right. So the area really hasn't changed. It's just shifted over 2 units. So it's still going to be an area of 2. All right, so the next one here is kind of a special case. So I'm going to skip number 7 and I'll come back to that. Let's look at number 8. 0 to 2 pi, and we have sine of x over 2. So again, transformation rules, that would be a horizontal stretch by a factor of 2. Remember, you have to take the reciprocal of the number in front of the x. So that would be a stretch by a factor of 2 horizontally. So I've essentially doubled this graph horizontally. But also notice my limits of integration, instead of going from 0 to pi, I'm going from 0 to 2 pi. So when you think about that graph stretched out, instead of going from 0 to pi, now it stretches from 0 to 2 pi. I've doubled the base. I haven't changed the height. That's going to give me an area that doubles an area of 4. Let's see, for number 9, we have the integral from 0 to pi of cosine x. Well, cosine x looks a lot like the sine x function, and I'm just going to graph it on here for you. So remember, cosine starts at 1. It would cross over the x-axis at pi over 2. So it essentially kind of look like this. And the area that I have above the x-axis, the area I have below the x-axis on that interval, they balance out and they'd add up to make 0. Okay, so let's go back to this one that went from negative pi to pi. So if I were to go from negative pi to pi, I know the answer is 0, and you can just see that on the graph, right? Because I've got this area here, I've got this area here. The areas are equal. One of them's below the x-axis, the other's above, so they're going to balance out. They're going to add up to make 0. But this is actually a special case because this is an odd function. And I want to talk about this one because this is something that you're going to see from time to time. Anytime you have an odd function and the limits of integration are symmetric about the origin, so I'll just say limits symmetric about origin, okay, so anytime you see this special case, you're always going to get an integral value of 0 because this is always going to happen. If it's an odd function with limits symmetric about the origin, you're always going to have equal area below the x-axis and above the x-axis, so it'll always make 0. The reason I want to point that out is anytime you see limits of integration that are symmetric about the origin, you should always be checking, is my function odd? Because sometimes you're going to get integrals that would be pretty hard to work out by hand, but if you can recognize it's an odd function, you don't have to work out the integral. You just have to know, oh, it's an odd function. I know it's going to be 0 because I have symmetric limits of integration. So be careful about that. That's something that'll show up from time to time. All right, let's take a look at just a couple of more here. If we have a constant value, so anytime we have a constant value for a function, that is going to create a rectangle. And I'm going to show you on this first example here. So it says, let's take an integral from negative 2 to 4 of 5 dx. Remember, that's essentially y is equal to 5 that we're looking at. Well, if I were to graph y is equal to 5, it's just going to go, it's going to have a horizontal line, right, that looks something like this. And if I go from negative 2 over to 4, all I've got here is a rectangle of area. So it's just going to be that region. And when I integrate, all I have to do is base times height. Well, the length of the interval or the width of the interval there is 6 units. The height is 5. So this is going to give me a value of 30. Okay, similar. On the next one, we have an integral from 0 to 8. And this time we have negative pi dx. Well, this you can kind of do in your head. If you just think about what would that graph look like? Well, y equals negative pi is below the x-axis. So we're looking at negative pi, and we have a width of our rectangle of 8 units. So this is just going to give me negative 8 pi. All right, and then let's look at just one application, a really simple application. And then I want to show you what primarily your assignment is going to look like today. So a train moves along a track at a steady 75 miles per hour from 7 a.m. to 9 a.m. Express its total distance traveled as an integral and then evaluate the integral. Okay, so we can already figure out the total distance traveled is going to be 150 miles, right? You can probably figure that out just by thinking about it. But from an integral perspective, what we would be integrating is our velocity function. It has a steady rate of 75 miles per hour. So the width of each rectangle would be dt, some time interval. And then how do we want to integrate this? Well, let's just say since it's from 7 a.m. to 9 a.m., we'll just go from 7 to 9. And that would give me essentially 75 times 2, and I would get a value of 150 miles. Interesting thing about these types of problems is you can always use your units to make sure you have them set up right. So with the 75 here, remember this was in miles per hour. dt would be in hours. So if I multiply miles per hour times hours, that gives me miles. So it's pretty easy to check when you have an application problem with integrals. It's easy to tell if you have it set up correctly based on the units. All right, so the last part here, you are going to have a lot of these types of problems on your assignment. Now, you're not going to have to draw a lot because we're working primarily in Math Excel, obviously. So I'm going to have you do some practice problems here because this is the way that you're going to solve a certain type of integral. So there's certain types of integrals that we can solve just by using areas. And when we solve these, we're going to be using, like, if you remember the one at the beginning, we're going to be using things like semicircles, triangles, rectangles, trapezoids, all really, really basic geometric shapes. We're going to use them to evaluate these integrals because when we graph them, the integral values are going to be represented by areas that are those simple shapes. Okay, so I'm going to show you one of these and then I'm going to have you try to work through some of them. So we have an integral from -1 to 1 and we have square root of 1 minus x squared. So we did one that was a lot like this. So what I want you to do on each one of these problems is I want you to sketch a graph and then I just want you to evaluate it from the graph. So hopefully you recognize this is a lot like the one we looked at earlier. This is a semicircle. And I'm going to go from -1 to 1. And so I'd end up with a shape that looks something like this. And then I'm just going to shade it in. That's the region that I'm trying to find. I know it's half of a circle with a radius of 1. So it would just be 1/2 pi times 1 squared. And that just gives me pi over 2. Okay, so that's all I want you to do on these. Now, keep in mind, if you have area that's below the x-axis, you've got to treat it as a negative. But other than that, it should be pretty simple for the most part when you do your calculations. So that's how I want you to set them up. By showing that graph, that's indicating to the person looking at your work that I am solving this integral by using area. So we're going to solve integrals using areas. We're going to approximate them with rectangular approximations like we did before. We're going to use what we call a trapezoidal approximation. And then we're also going to use something called the fundamental theorem of calculus. So we have a lot of methods for solving integrals. And this is one of the methods that works when we get these really kind of perfect geometric shapes. Okay, so I want you to pause the video and I want you to take about 10 minutes or so. And I want you to work through the rest of the problems here. And when you come back, I'll just go through the solutions with you. Okay, and here are the answers that you should have ended up with. On the next one, it was just a constant. You may not have even needed to graph that one. So you would get a rectangle, and the length of the interval there, or the width of my rectangle, would be 8 units. Height of the rectangle is pi, so 8 pi. Okay, now we have absolute value of x minus 3. And you can see I ended up with 2 triangles here. So I found the area of each triangle, added them up, got 5 over 2. Next one here, we have 2x minus 4. You can see we have area that's below the x-axis and area that's above. So I always do what's above minus what's below. You can always do negative 1/2 times 4 times 8 plus 1/2 times 1 times 2. But I like to just put it in the order where it's the positive minus the negative, and then I don't have to worry about that. Either way, it's 2 triangles, very simple to do. Okay, next one here, we actually get a trapezoid. So remember with the trapezoid, it's 1/2 of base 1 plus base 2 times height. That's all I did there. Next one, when you can use symmetry on these, a lot of times you can save yourself some work. So we have negative absolute value of x minus 4. And all I did here was I recognized that I have two trapezoids, and this is a function that's even, so it's symmetric about the y-axis. And I know the result's going to be negative. So the easy thing to forget on this is the negative. I just put it out here in front because, yes, I'm thinking about area, but because it's below the x-axis, I've got to have a negative there. And then I just did 1/2 base 1 plus base 2 times height. And then obviously the 2 out in front was because there were two trapezoids. All right, so for this one, this is kind of like that sine function we were looking at earlier. We have the square root of 144 minus x squared, and then we did plus 1. So by adding a constant, I'm translating that graph up by 1 unit. That's going to create a rectangle underneath that semicircle. And so you can see essentially I have a semicircle plus a rectangle, and the semicircle is the 1/2 pi times 12 squared, and then my rectangle is just 24 times 1. All right, next one here, we've got negative 4 to 4, absolute value of x plus 10. Again, we have an even function. It's just two trapezoids. So I found the two trapezoids, area of 96. Now, these ones are a little different from 0 to b. So we just have some arbitrary value b. So that means my solution is going to be in terms of b. And what I did was I created my graph of 4x. I went b units to the right. That means I would go up 4b units. And I'm still calculating the area of a triangle. I'm just doing it in terms of b. And then this last one, although it looks really messy, it's actually really simple when you think about it geometrically. We're going from a to square root of 3 times a. And I've got y equals x as my function. So the base of that triangle is square root of 3 times a minus a. And then the height is going to be, or excuse me, this is my height. What I have right here is the height of my trapezoid. And then the bases of my trapezoid are right here. This would be like base 1 and base 2. And then the 1/2 is out in front because we're dealing with the trapezoid. So still just dealing with area of a trapezoid, but very simple, just writing it in terms of a as opposed to getting an actual numerical value. Okay, so that's really what I want you to focus on for today. And then next time we'll talk about a couple of little details when we're doing integrals by area that we can think about.